Alright, in this video we look at spherical coordinates, okay? And here are the formulas for spherical coordinates. Z is equal to rho cosine phi. X is equal to rho cosine theta sine phi. And Y is equal to rho sine theta sine phi. So what we're seeing here is a transformation that depends on rho, theta, and phi. These three variables are the spherical coordinates, and we're seeing that x, y, and z is given by rho cosine theta sine phi. Y is equal to rho sine theta sine phi, and z is equal to rho cosine phi. There are many different ways of writing spherical coordinates depending on your preferences. This is the preference that we will use excuse me, in math class. Okay, we'll need to talk about the meaning of these spherical coordinates and what their interpretation is, but I thought I would first start with trying just to give you an idea about why these are called spherical coordinates in the first place. So if we consider the equation of a sphere, right, we recognize that x squared plus y squared plus z squared is equal to 4 is the equation of a sphere of radius 2. And if we take that x is equal to rho cosine theta sine phi, as has been dictated by this transformation, y is equal to rho sine theta sine phi, and z is equal to rho cosine of phi squared. If you were to square these out, you would get rho squared cosine squared of theta sine squared of phi plus rho squared sine squared of theta sine squared of phi, right? Plus rho squared cosine squared of phi is equal to 4. And if you can see here that the sine squared phi is common, right? So we will factor that out, sine squared of phi here. And then the rho squared is in common, so we will factor that out also. And then you have cosine squared of theta plus sine squared of theta. And then finally over here we have rho squared cosine squared phi is equal to 4. All right, now this is the Pythagorean identity that we recognize. It's equal to 1. So that will lead you to rho squared sine squared phi plus rho squared cosine squared phi is equal to 4. Okay, the rho squared is in common, so we can factor that out. And that will lead to rho squared, and another Pythagorean identity, sine squared plus cosine squared is 1. So this leads us to rho is equal to 2. So this might give us an idea that this was a sphere of radius 2 in Cartesian or rectangular coordinates. And then when we did the conversion of that sphere to spherical coordinates, we got rho is equal to 2, which is the same as the radius of the sphere. So what we're seeing here is that rho is the radius variable. This is the spherical coordinate that describes the radius of the sphere. Okay, so what we're going to see over here is a demonstration of the different spherical coordinates. Okay, now in this demo, r is equal to the variable rho. Okay, so what we're seeing here is that if you change the variable rho, we are getting something, a shape that is getting smaller in size, for example. Okay, and there are two angle variables, theta and phi, and if you look at the variable theta, Alright, so we're looking at the variable theta and trying to figure out what it looks like and what its interpretation is. So we can see here that theta is changing, and it's the angle. As it was in cylindrical and polar coordinates, theta is the angle that is measured from the x-axis in the counterclockwise direction, right? And then we have the variable rho, which is controlling the radius, okay? But it's the radius of what? It will be the radius of a sphere, as we will see in just a second. This currently looks like a cone, but there's another angle, phi, and in mathematics, in the formula that we've got over here on the right, z is equal to rho cosine phi. Phi is the angle that's measured from the positive z-axis, and it's measured downward in the clockwise direction. So here is phi getting bigger and bigger and bigger. Here is phi is equal to pi. Okay. And if phi continues on, if phi equals pi over 2, and if phi gets to be equal to pi, 3.14, we now have our sphere. And if theta is less than 2 pi, so this is 6.282 pi, if we let theta get a little bit smaller, we can now see our sphere opening up, and the radius rho changes the radius of that sphere. Okay. If we choose to pick some of these variables equal to a constant, let's let rho equal to a constant, you will know it will no longer have a solid region as we are seeing here. We will have only two variables that can change, and in this case we're seeing that rho is equal to a constant, which means that we have the shell of a sphere. Okay, and if that angle gets bigger and bigger, we can close the shell up. Okay, or if you adjust phi, we can make the shell kind of melt from the bottom up. Right, so here we have a way to describe the, maybe not the whole part of the sphere, but maybe just a part, maybe the cap, the top part of the sphere. Okay, now if you let rho be now a variable, we should see that we now have a cone again. Okay, and if theta is equal to a constant, can we imagine what we're going to get? If theta is a constant, that means we're going to pick a certain value of theta right here. Okay, so we went from this edge of the sphere, go around an angle theta, and if you fix that value of theta and radius still changes, okay, so we're getting a slice of that cone, and if phi gets bigger and bigger, we can make, maybe a fan shaped or a slice, half a slice of the sphere. Okay, and if theta is still a fixed number, but theta is a different value of theta, we're just getting like this little weather vane pattern or weather vane shape that's just kind of blowing around perhaps in the wind. Okay, now let's let all the variables come back in and be in play. So notice that the radius of the sphere is going from 0 to 1. That's why we're seeing a sphere of radius. We're seeing the ones and negative ones. We're seeing theta go from 0 to 2 pi, and we're seeing phi go from 0 to pi. So that gives us the whole solid ball. This is a solid region. Okay. If you fix the variable phi, phi being equal to a constant, okay, let's see what happens here. So if phi is equal to a constant, right, and then theta goes all the way around from 0 to 2 pi, we get the equation of, or we get a cone shape that you can fill up with snow cone, icy material, or whatever you want. Ice cream would be my preference. So as the radius changes, the cone gets a little bit smaller. Okay. So these are the different things that can come about, especially a cone. Even though we're talking about spherical coordinates, I mean, that doesn't mean that you have a spherical region. We can describe different regions.
I found this on the web for spherical region. Check it.
Sorry, Siri overheard me. Let's see. So we can describe regions that aren't spherical in nature with spherical coordinates, like cones, for example. Okay, so there's an introduction to the spherical coordinates. We have one radius variable, one angle measured in one radius measured in meters, and we have two angles probably measured in radians. All right, and what we're going to need to do here is to be able to compute triple integrals of some function over a region D in three-dimensional space, dV, right? And if we would like to do these kind of integrals in spherical coordinates, we're going to have to do something d rho, d theta, d phi, right? But we can see that this is supposed to be, dV is supposed to have the units of volume, meter cubed, right? But we can see that only one of these is measured in meters. The radius is measured in meters. And these angles, d theta and d phi, are measured in radians. So we need some sort of fudge factor that is going to compensate and turn radians into meters. And so what we have here is a fudge factor, the determinant of the Jacobian of this transformation here. If you look at the determinant of the Jacobian of that transformation, you will get rho squared sine of phi. And that is the fudge factor that is going to be needed to compensate and turn the radians, along with this quantity here, will turn the rest of the units into meters squared to make our final dV units come out to be meter cubed. So ends an introduction to spherical coordinates.